Welcome to Lecture 7.2, Nonstandard Inner Products and Gram Matrices. As a warm-up, consider an n by m matrix A over the real numbers where the columns are vectors x1 up to xm. The m by m square matrix A transpose A is self-adjoint. We've already seen that. And remember that the ijth entry of A transpose A is xi transpose times xj. So you can really think of this matrix as the matrix of dot products of all pairs of these vectors xi. Recall that A and A transpose A have different domains. So A goes from am to an, whereas A transpose A goes from am to itself. Let's summarize a few important points about the matrix A transpose A. First off, A and A transpose A have the same rank and the same nullity. Even more than that, they actually have the same null space. So not just the dimension is the same, but the actual null space is the same. We've proven that. We've seen that A transpose A is non-negative, and it's positive if the vectors x1 up to xm are linearly independent. We've seen that if the null space of A is trivial, or equivalently, if the columns are linearly independent, then the projection matrix onto the span of those columns is A times A transpose A inverse times A transpose. Later in this section, we will diagonalize A transpose A to get the celebrated singular value decomposition of A, which comes up in many applications in applied math and statistics. So the takeaway here is that this is a very important matrix. It can be really thought of as the true way to square a matrix. And when I say that, I mean you could of course square a matrix, but you might get complex or negative eigenvalues. This way you get non-negative eigenvalues. And one reason why it's so important, well, in addition to this first property, really why this holds, is because it is the matrix of all dot products. And that's what we are going to generalize in this lecture. So let's do that now. We'll generalize the construction of A transpose A, which you should be thinking of as the matrix of dot products. We'll see that every positive matrix has this form. It can be thought of as a matrix of inner products for some vectors and for some inner product structure. And this is perhaps a little surprising because the property of being positive does not depend on the inner product structure at all. It actually depends just on the structure of the linear map because it depends on the eigenvalues. But the matrix of inner products depends on both the choice of basis and on the inner product structure. It's time for a definition. The Gram matrix of m vectors, x1 up to xm, is the m by m matrix where the ijth entry is just the inner product of xi with xj. Notice that G is simply the matrix A star A, where A is the matrix whose columns are x1 up to xm. Let's now prove what I've basically already claimed. First off, that every Gram matrix is non-negative, so there's nothing special about A transpose A. Here we just used the standard inner product. But remember that if we pick an orthonormal basis, then any inner product we deal with can be written as dot products. Next, the Gram matrix of a set of linearly independent vectors is indeed positive, just like what we had for A transpose A. And finally, every positive matrix is a Gram matrix. So what we will do is, given a positive matrix, we will show how to construct an inner product, a new inner product, so that this matrix is the Gram matrix of a collection of vectors. let's get started with that right now. Let's prove this now. In fact, we can do 1 and 2 together in basically one line, except that line is going to be a little bit notationally messy. And because of that, it's going to hide some of the intuition. So I'll do that line first, and then I will unpack it and draw it in like matrix and vector form so you can really understand what's going on. So let's take a vector z, and we need to show that the inner product of z with gz is non-negative. So remember, let me write it up here, inner product of z with gz, that is gz conjugate transpose times z. So that's z conjugate transpose, g conjugate transpose times z. So if we write this out, this is the sum over n squared terms of the form zi times gij bar times zj bar. And so by definition of this matrix, I'm just going to plug in what this is. This is the inner product of xi xj times zi times zj bar. So again, this is the sum of n squared terms, but we can write it as an inner product of two vectors, I equals 1 up to m of, I have to be careful here, this is zi, these are the coefficients, times xi, and the sum from I equals 1 up to m of, or actually I'll call this j, so zj times xj. And this, notice, is the norm squared of this vector. So j equals 1 up to m zj x xj. And that is automatically going to be non-negative. And moreover, if the xi's or the xj's are linearly independent, then this is going to be this is not the zero vector, so it's going to be strictly bigger than 0. And so that's why the Gram matrix is positive if the xj's are linearly independent. So if you believe this, we've proven 1 and 2. But you know, whenever you have these double sums and these double subscripts, it's not, you really have to pause every single step so you can verify that, and you don't really get the full intuition. So that's what I want to do now. So what is this really saying? So let's write this in matrix notation. So z, the inner product of z with gz, I'll write it like this. So this is z1, z2 up to zm. And then what I have here, I have z1, z2 up to zm, and I really should put bars here. And then the entries here are of the form, so this is x1, 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 x2 up to xm, xm. And down here we have xm, x1 all the way up to xm, xm. So we have this matrix, and it's not clear what to do with this to how to get this norm squared here. So what I'm going to do is start here and work backwards and kind of meet in the middle. So now maybe this notation can be improved, but the zj's are coefficients and the xj's are vectors. So clearly this norm squared is just this inner product. So let me expand that, and I'll do that down here. So this is z1 x1 plus ... zm xm the inner product of that with itself. So z1 x1 plus zm xm. And if I were to give you this and I say, how would you evaluate it? Well, you use bilinearity and you break this up into n squared terms. And the terms are going to be the inner product of zi xi with zj xj. And using the definition of the inner product, what we are going to get is zj xj. These are bars, and this should be a transpose with zi xi. And again, these are vectors and these are scalars. But notice that that's really what I have here, and I don't think it's a stretch to see why that's exactly what this is as well. So again, I haven't proven it completely this way, but I did this one-line proof, and I think you can see the intuition as to what's going on when you write it in matrix notation, because we start out with this and we end up with this, and it's not too hard to fill in these gaps. Finally, for part 3, before I do it, let me give you the intuition. So I'm going to write a matrix H11, H12, H1m. Say this is an arbitrary positive definite matrix. So this is HMM, and this is HM1, and so forth. Now look what happens if I multiply here by the jth unit basis vector EJ, and then EI transpose. So if I do that, I literally just pick off the HIJ entry. So I'm going to define an inner product. So the inner product of EI and EJ, if I can define an inner product where this is HIJ, then I'm done. So I will define what I call the non-standard inner product of EI and EJ to be based on my default inner product, the inner product of EI and H EJ. Because H is self-adjoint and positive definite, this is an inner product. And I claim that in this case, the inner product of EI and EJ is indeed HIJ. And I'll let you check that using this definition. And it may look like that I put using this definition, you say, oh, well, the EJ should be over here and the EI should be over here. That is true, but then we have to take the conjugate transpose of this as well. So this is indeed equal to HIJ. So given an arbitrary positive matrix, we have defined an inner product and with respect to this inner product, this matrix A is our matrix of dot products, or our matrix of inner products. Now for fun, I want to show you 2 examples of Gram matrices that arise from vectors in infinite dimensional spaces of functions. To begin, let X be the space of real valued functions on the interval 0, 1, where the inner product of f and g is just defined to be the integral of their product on 0 to 1. If we take the m vectors that are the smallest powers of t, so t to the 0th, t to the 1st, up to t to the m minus 1, then the corresponding Gram matrix is G, where the ijth entry is easily computed by just integrating t to the I minus 1 times t to the j minus 1, 0 to 1, and a very simple calculus exercise gives us that that is 1 over I plus j minus 1. For a more familiar example, consider the space of complex valued functions on 0 to 2 pi. If you prefer, you can think of these as periodic functions on the real line. And let W be a weighting function, so a positive function on 0 to 2 pi. We saw this when we studied Sturm-Liouville theory, and generalized Fourier series a couple of lectures ago. So given that, define the inner product of f and g to be the integral on 0 to 2 pi of f of theta, g of theta bar times w of theta d theta. If fj is the complex exponential e to the j theta for, well, let's take finitely many of them. So let's say j equals negative n to positive n. So this isn't, here we have 2n plus 1 vectors. So the gram matrix is 2n plus 1 by 2n plus 1. And I don't want to call the entries Gij again because I is now the square root of negative 1. So let me call it Gkj. And so the kjth entry is a Fourier coefficient, namely Ck minus j. And remember the formula for a Fourier coefficient. C omega is the integral from 0 to 2 pi of omega of theta e to the negative I omega theta d theta. And this is negative because it's the complex conjugate of this, or of this function. Okay, so if you want to know more about this, there's a lot more I could say about this. I would actually encourage you to go back and watch that video on generalized Fourier series and Stroum-Liouville theory. Moving on, I want to revisit this idea that we did a couple slides ago about defining a new inner product using a positive definite matrix. So if X is a vector space with inner product that I will denote with parentheses, a positive map M defines a so-called non-standard inner product that I will use with angle brackets, defined as follows. So the new inner product of X and Y is the old inner product of X with My. Now I've done examples like this previously in the course. I just haven't called it this because we didn't really have a use to call it this until this lecture when we wanted to prove that every positive matrix is a gram matrix, and we're going to continue with this. But first, I really want to emphasize an important point, and that is that being self-adjoint is a property of the inner product structure. So there's going to be linear maps that are self-adjoint in one vector space or one inner product space, but not in another, or vice versa. So here's a lemma. I said as a homework. I think I'll do it because it's very simple. So if H and M are self-adjoint with respect to some inner product, and M is positive, then M inverse H is self-adjoint with respect to the non-standard inner product defined above. And to see why this is, it basically follows pretty simply. Let's write out what, so for this to be self-adjoint, let's write the inner product of X and M inverse H, X. And let's go back to our standard inner product. So X dot M times M inverse HX. Of course, this cancels to get inner product of X and HX. And now let's see, for this to be self-adjoint, we have to put it in the left coordinate and see that we get the same thing. So M inverse HX dot X in our non-standard inner product. Let's bring it back to our standard one. So that's M inverse HX MX. And if M is self-adjoint, then we can move it over here and get M inverse HX dot X, or just the inner product of HX and X. And we know that these two are the same because H is self-adjoint. Let's explore this a bit further. If being self-adjoint depends on the inner product structure. That means we can probably find a linear map that's self-adjoint with respect to one of these but not the other. And so let me just take H, which is self-adjoint with respect to the standard inner product. And I claim that H is probably not going to be self-adjoint with respect to this non-standard inner product. And let's explore. So x dot hx, the new inner product, is the old inner product of x dot mhx. And if we put h in the other coordinate, we're going to get hx dot x equals, parentheses, hx dot mx. And now if m is self-adjoint, we can, so m and h are self-adjoint, so I can move m over here. Actually, let me move h over here, and I'm going to write this as inner product of x with h inverse mx, and it's generally not going to be true that mh is equal to h inverse m. So if you find any matrix A that for which this does not hold, then H is not going to be self-adjoint with respect to this new inner product. Now let me give you a geometric way to think about this. Let's say that we have a 3 by 3 matrix, because that's really the most we can visualize geometrically, and it's got 3 eigenvectors. I'm going to draw them like this. Say x1, x2, and x3. So if these are not orthogonal, with respect to the standard dot product, then that matrix is not going to be self-adjoint or symmetric. However, we can certainly define an inner product structure where these vectors are going to be orthogonal. And in that case, with respect to that inner product structure, the matrix is going to be self-adjoint. Because remember, the way to think about what a self-adjoint matrix is, I've said this multiple times and I will continue to say this, is if you tilt your head in the right direction, think of the linear map 2, 3, 4, the diagonal matrix. It stretches this direction by 2, this direction by 3, and then this direction by 4. In other words, it sends the unit cube to a rectangle, or sorry, a box, a rectangular box, rather than some parallel pipette. So when I'm saying rectangular versus parallel pipette, I'm saying any two of these vectors are going to be orthogonal, and that depends on the inner product. So even if, to our standard Euclidean eyes, if this looks like it's not orthogonal, if you put a geometry on it where these things are orthogonal by finding the correct inner product space, then when you apply the linear map, you're just, and if these are the eigenvectors, you're just going to stretch these out or squash them by something, and just geometrically you can see that what you're doing is what I'm describing up here, just with a different geometry. So this is a self-adjoint map with respect to that new inner product. So takeaway message is that the property of being self-adjointness is dependent on the inner product structure. Moving on, let's continue with self-adjoint maps H and M and a positive M. We can define the so-called generalized Rayleigh quotient to be R sub H comma M of X, the quotient of the inner product of X and HX with the inner product of X and MX. Now this may look a little bit out of left field, but let's work with it a little bit. If I rewrite this by sticking in an M inverse up here, then I can rewrite this with a non-standard inner product, namely the inner product of X and M inverse HX over the inner product of X with itself, with the non-standard inner product. And this is just the Rayleigh quotient of M inverse H with respect to this inner product. So in other words, the generalized Rayleigh quotient is a standard Rayleigh quotient in a different inner product space. So this is very non-standard notation, but to distinguish between the two inner product spaces, instead of using parentheses to denote the argument, I'm going to use angle brackets like this. Now, another possibility is to put the angle brackets or the parentheses as a superscript, but I think that just gets too messy. I like it like this. So several easy comments. The ordinary Rayleigh quotient is simply the generalized Rayleigh quotient with respect to the identity map. And next, something I just said, but I want to emphasize, the generalized Rayleigh quotient is an ordinary Rayleigh quotient, just with a different inner product structure. What this means is that all of the results that we have proven for the ordinary Rayleigh quotient carry over to the generalized Rayleigh quotient. We just have to interpret them in the right inner product. So I'm going to go through and re-summarize them. Please watch the video on the Rayleigh quotient if you have not already. Otherwise, this is really going to come out of left field. So once again, this is just the definition. I'm writing it up here for reference for what I'm going to show you next. So the minimum value of the Rayleigh quotient is the smallest eigenvalue. So for the standard Rayleigh quotient, it's lambda 1, where HV1 equals lambda 1V. The generalized Rayleigh quotient has a minimum value, let's say mu1, which is the smallest eigenvalue of M inverse H. So formally that means M inverse H W1 equals mu1 W1 for some eigenvector W1, and often this is written as H W1 equals mu1 M W1. Let's think back to what we did with the standard Rayleigh quotient. We found its minimum value, and that occurred on an eigenvector, so we took the n minus 1 dimensional complement of that eigenvector. We called it x1, so the complement of that eigenvector line, and then we found the minimum of the Rayleigh quotient on that space, and that was the second smallest eigenvalue. And we just iterated that process. So let's iterate that same process, but with a generalized Rayleigh quotient, which really is the standard Rayleigh quotient with a different inner product. So x1 is the orthogonal complement of this eigenvector. So x is the direct sum of this n minus 1 dimensional space with that eigenvector line. And the minimum value of the generalized Rayleigh quotient on the subspace x1, let's call it mu2. It's the minimum, remember we only need to look at unit vectors, of the function of the standard Rayleigh quotient with respect to this non-standard inner product, restricted to all vectors that are orthogonal to v1. And that's the definition of x1. So if we interpret this back to our standard inner product, we get the minimum over all unit vectors of the generalized Rayleigh quotient, restricted to all vectors x that are orthogonal to m to v1, m times v1. And here, mu2, regardless of the inner product structure, is an eigenvalue, say of eigenvector W2 of M inverse H. So M inverse H W2 equals mu2 W2, and this is the second smallest eigenvalue of M inverse H. Once again, I'm not proving this. We did the proof for the standard Rayleigh quotient. I'm just interpreting the results in terms of the generalized Rayleigh quotient. Recall from the lecture on the Rayleigh quotient that we also had a so-called min-max principle. So if we had a self-adjoint linear map with eigenvalues in increasing order, lambda 1 up to lambda n, then the kth smallest eigenvalue was the minimum over all k-dimensional subspaces of the maximum Rayleigh quotient on that subspace. So again, I'll refer you back to the original lecture for some examples of this and some motivation. But let's let's now interpret what this says about the generalized Rayleigh quotient. And I will leave the details as a homework exercise. Just like we did in the last slide, it's not really anything new, it's just interpreting our old results. So I will state them here. Suppose H and M are self-adjoint and M is positive. Then there exists a basis, V1 up to Vn, of X, so where each Vi satisfies the following. HVi equals mu I mvi, where mu I is real, and the inner product of Vi with mvj is 1 if I and j are the same, and 0 if they are different. Now the reason why this is true, what this is really saying, is that this basis is orthonormal with respect to the non-standard inner product. That is, if x and y, the inner product of this is x dot my. Because think about what this is saying. This is really saying that m inverse h vi equals mu I vi. So this is a basis of eigenvectors of m inverse h. And what this is, and this looks like, on the right, it looks like the orthonormal condition, and it is, because this right here is just the non-standard inner product of Vi and Vj. Also on your homework, I want you to compute the inner product of Vi and HVj. It might be easier to think of this as in terms of the non-standard inner product of Vi and M inverse HVj, and show that there is an invertible matrix U for which U star Mu is the identity and U star Hu is diagonal. And finally, I want you to characterize the eigenvalues mu1 up to mun by a minimax principle like this up here. So again, don't reprove it, just use the existing one and interpret this starting with the non-standard inner product and then write it in terms of the regular inner product. I'll conclude this lecture with a surprising result about positive matrices that really follows from what we did on Gram matrices. I put it at the end because I really wanted to not break up the flow about the non-standard inner products from Gram matrices to the generalized Rayleigh quotient. So this is about the Hadamard product of matrices. So if A and B are the same size, then imagine how someone who has never learned about matrices before is going to try to multiply them, probably entry by entry. So if A is, say, A11, A12, A21, A22, and B is B11, B12, B21, B22, and the Hadamard product of A and B is you just, again, you multiply the corresponding entries, almost like you're taking a dot product. Well, I guess it's not a dot product because what you end up with is not a scalar. So so it's A11, B11, A12, B12, A21, B21, A22, B22. Schur's product theorem says that if A and B are positive, so they have to be square for that, then their Hadamard product is positive as well. And this is something that you really should not expect. It should come as a surprise because it's not clear at all in what we've done this entire class what the meaning of this product is. But the key here is to use the theory of Gram matrices. So since A and B are positive, they are Gram matrices. All we have to do is show that this matrix is a Gram matrix as well. So let's write A, which is Aij, as a Gram matrix. So we have some vectors u1 up to um in an inner product space U, so ui dot uj. I still like to write this, I like to visualize it like this, u1 dot u1. It helps me to see it like this. u1 um, then we have um dot u1, dot like this. And then B is bij. This is a gram matrix, so in some other inner product space, the inner product structure is generally going to be different. We have vi dot vj is the ij entry, and so once again this is v1 dot 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 v1 vm v1 and vm dot vm. I'm just writing this because I like looking at it. This is v1 up to vm in some v. Now I'm using the same notation for both inner products. I think it's clear from the context. You know, some people like to use one of them, use brackets for one, or maybe a subscript u and v. But I think that would only make it just more messy. So the trick here is to consider is given this. Let's consider the tensor product. You probably didn't expect this to come up, of u and v. And one thing that I have not said, I think I will in the future leave this as a homework exercise, is to understand what the inner product structure is on the tensor product. So again, tensor products are fairly abstract. It's often helpful if you have ui tensor vj. Sometimes it's helpful to think about this as like x to the I times y to the j. You really are multiplying the base. You're creating a new vector space where the basis elements are the products of things in here and things in here. So a lemma that I will leave as an exercise is that u tensor v inherits an inner product structure from u and v, where, and we can define it on pure tensors, where the inner product of u tensor v and u prime tensor v prime is the product of u tensor u, sorry, the product of the inner product of u and u prime and v prime. So you're multiplying, think of it like variables in x and variables in y. So in terms of the inner product, you just multiply the corresponding inner products together. You got to check that this works. Some of the, I think bilinearity is the hardest thing to check, but it's pretty, the other properties like symmetry are pretty easy. Okay, so now what? So we're trying to show that the Hadamard product of A and B is positive. So this is A ij, B ij, and that's just the product of ui.uj and vi.vj. So let me write that as, so that is the matrix where the entries are ui.uj and vi.vj. Now look at this definition of the inner product here. We can go backwards. We can write this as the inner product of the tensors. So this thing right here, I'm going to write this as ui tensor vi dot uj tensor vj. I'm going to write it like that. And now we see right away that this is a gram matrix. So it is positive definite. And just to think about what this is, so this matrix is, I'm going to write it like this. G1 dot G1. So what we've basically done is showed that this is a grand matrix. So G1 dot G1, G1 dot GM, GM dot GM, GM dot G1, where G1 equals U1 tensor V1 all the way up to GM is UM tensor VM. So let's put the box right here. Coming up in the next few lectures, we will talk about two common decompositions of matrices. There's the polar decomposition and the singular value decomposition, which we mentioned at the very beginning of this lecture briefly. So stick around.